So this is the first video in our second unit where we're looking at forces in motion, and this will be a short video. We're kind of going to define what force is, what different types of forces there are, and talk about how we model forces acting on an object using free body diagrams. So a force, we're going to define it as a push or a pull. So a force is really kind of like an external interaction between two objects or systems, and despite any better definition, we're going to just define it as a push or a pull. So that's pretty easy to think about. So if you're pushing or pulling on an object, like with an applied force, that would be a force, but there's also like fields, like gravitational field or the electromagnetic field that can produce a force. So the units of force are the Newton, the SI units, and if we express the Newton in terms of the base SI units, 1 Newton is equal to 1 kilogram meter per second squared. And when we look at Newton's second law, we'll realize why the units are the way they are. Here in the US, we use pound as our unit of force, and the Newton is pretty small. 1 Newton is equal to 0.225 pounds. Okay, so the forces are what kind of cause objects to move or change their motion. So the net force acting on an object means the sum of all the forces acting on the object. So the combined effect of all the forces exerted on the object. So if we have two movers that are moving this large box, okay, we have a push and a pull, but those are not the only forces that we have to consider, because those are not the only forces acting on the object, on the box. Those are the two kind of obvious ones, but we also have a friction force. If the box is moving, we would call that a kinetic friction force. If the box hasn't moved yet, like if it's not moving yet, then we would call that a static friction force. We also have gravity acting on the object. Any object on Earth is going to have a gravitational force if it has mass. And there's also a normal force, so the floor pushing back up on the box, that reaction force due to that gravity force pulling down. There's reaction force on the box up, keeping the box on the floor. Okay, so because forces are vector quantities, when we look to sum up all those forces, we have to split them into the forces that are acting in the x direction, or the components of the forces that are acting in the x direction, and the ones that are acting in the y direction. So here, the way we've drawn this picture, all these forces are either acting directly in the y direction or in the x direction. Okay, so if we were to sum up all these external forces, it would need to be the vector sum. So we can't just add up all of these forces. We would have to split them into the x and y direction. So we would have a net force that has an x component that we get from summing all these forces in the x direction. So this push, the pull, and the friction force. Okay, notice that friction force, I put a minus sign because in the reference frame here that I've set up, the positive direction is to the right. Okay, and then we would also need to sum all the forces in the y direction. Okay, here we just have two forces acting in the y direction. Gravity is pulling down. The normal force is that reaction force of the ground pushing back up on the box. And so in the way we've identified our reference frame, up is the positive direction. So we would do that normal force, Fn, minus the gravitational force, Fg. Okay, so if we, and I didn't put numbers to these, but let's say that when we look at this, the push and pull kind of are a little bit more than that friction force. So if you add those together, it's a little bit more than that friction force. It's more than that friction force, so we have a net external force. Okay, that normal force and force of gravity cancel each other out, because the normal force, when the surface contact is the surface of the Earth, and it's parallel to, like, it's not an incline, so it's just like a horizontal surface, then your normal force and gravity force are going to be equal and opposite of each other. So those canceled out, and we're left with just a net external force acting to the right. And so that is the force that's going to cause this box to move. And you'll notice I show that net external force is acting on the center of mass of the object. Okay, so when we're modeling these, we're going to model that all these forces acting on the object are acting through the center of mass. Okay, well, an object like this that you might end up with some torque, but we're not looking at that yet. We're just going to model it as everything is acting through that center of mass. Okay, so if we do have a net external force, we are going to change this object's motion, and it will be accelerating in the direction of that net force. Okay, so looking at the example we just looked at, there was gravity, the force of gravity, there was a normal force, there was a push and a pull, a force of friction, and we're going to go over the different types of forces that we're going to talk about in this class. First, we're actually going to go over the 4 fundamental forces, and then we'll talk about like contact forces, like the applied force of a push or a pull, friction, drag, tension, the other types of like contact forces we're going to look at in this class. So the 4 fundamental forces, the one you're most familiar with is going to be gravity. Okay, so gravity acts between any 2 objects that have mass. It's an attractive force between any 2 objects with mass. Okay, directly proportional to how big they are and inversely proportional to how far they are apart. Okay, so that's the one we're probably most familiar with. The electromagnetic force is also a non-contact force and one of the 4 fundamental forces, and that is the force that acts between charged particles, either moving or non-moving charged particles. When you have non-moving charged particles, there's an electric field, an electric force, and when you have moving charged particles, you have a magnetic field or magnetic force that is produced. And at first we described those as 2 different fundamental forces, but they are kind of one and the same. So we call it the electromagnetic force. Okay, the strong nuclear force is the force that holds protons and neutrons together within the nucleus of atoms. Okay, and the weak nuclear force is associated with radioactive decay or like beta decay. So those are the 4 fundamental forces. I think the weak nuclear and electromagnetic have been like merged into the electroweak force. And some physicists think that there's like a unifying, that we could combine all of these forces into like one unifying universal force, but we're not there yet. So those are the 4 fundamental forces. Okay. In this class, we're going to talk about contact forces, and a lot of these contact forces are actually due to the electromagnetic force. Like when I put my hand on the table, it's not going to go through the table because the electrons in my hand are repelled by the electrons in the table. Okay, so, but there's lots and lots and lots and lots and lots of electrons, so it's useful to think of these as just kind of different types and the contact forces. So we're not going to really describe it with the same way we do electromagnetic forces, even though that's what they're like, a combination of a bunch of those electrons and that electromagnetic force or electric force, repulsive force between the electrons in 2 objects. Friction is another thing. You got that's also kind of like a manifestation of the electromagnetic force, but we don't really in physics treat it that way because it's easier to think of them as contact forces when 2 surfaces are in contact. Okay, so we have applied forces. So, and they act as indicated on the object. So in our example of the 2 people moving the box, we have a push and a pull. Those would be applied forces. So we could say applied force 1, and then he applies a force on this rope. And the rope is actually what applies a force on the box. So that would technically on the box be a tension force, but he's pulling on the rope. So the pull on the rope would be an applied force by this person 2 over here. Okay, we also have normal forces. I'm also giving you just kind of the variable we use for these. Normal force, you can see Fn or sometimes just uppercase N to denote that it's a normal force. And the normal forces always act perpendicular to the contacting surface. Okay, so if that's a horizontal contact surface, it'd be straight up. Okay, however, if you move that contact surface at an angle, okay, now your normal force is not going to be acting straight up anymore. It's going to be perpendicular to that contact surface. Okay, we also have friction forces. Okay, those act parallel to contact surfaces and always resist the motion. Okay, so if you're applying a force on an object, I guess I don't really have, anyway, we'll look at the picture. Okay, so they're applying a force in this direction. That friction force would never be an additive force and propel the box, right? That friction force is going to resist that motion and going to be acting back in the opposite direction of the way that they're pushing them. So it resists relative motion. Okay, and you actually have two different types of friction well, there's multiple types. Like drag could be considered a type of friction, like air friction. But when you're looking at two objects in contact with a contacting surface, if they're not moving with respect to each other, we will call that static friction. If they're moving with respect to each other, then kinetic friction is what we call that type of friction. And you'll when we move to the next part of this unit and look at friction in more detail, we'll find that the static friction force, actually the maximum static friction is actually higher than what that kinetic friction would be. And if you've ever like moved or slid a box along the floor that's really heavy, you may have realized that once you start pushing, it actually becomes a little bit easier. You don't have to really push as much to keep it moving, but you do have to overcome that static friction, get a big oomph to get it actually moving. Okay, so force of friction kinetic, you might see just FK or FRK, or an FRS. It's for force of kinetic friction and force of static friction. Okay. Tension is the other one we're going to look at in this unit. So tension acts along a taut rope or string or wire, and it pulls on objects at both ends. So a rope cannot push, right? It would be silly. I can't push this rope, right? If I try to push that rope, nothing happens. The rope just goes slack. But I could pull on this rope and pull this object. Okay. So tension always is a pulling force, and it acts at both ends of the rope with an equal force. Okay, so let's talk about how we model forces. Okay, so in this example here, we previously just kind of drew the arrows on the box, but instead of drawing a detailed picture, we have something called free body diagrams that are a simplified picture of what's going on that shows the object and the forces acting on the object. Okay, so how we would draw this box with a free body diagram, we will model the center mass of that box, either with, you could use a circle or a square, but we're gonna draw arrows indicating all the forces, and those arrows are connected to the box or circle, whatever you've used to model that center of mass. And then all the forces are labeled with their variable, okay? And you may see them labeled with the actual numerical value for each of those forces as well. That would also be a valid free body diagram, okay? You do want to also include a reference frame, so you know which direction is positive for your X and Y components, or you could add, if you had a Z axis too. But in this class, for the most part, we're going to stick with two-dimensional situations. Okay. Oh, and actually, I could also draw the acceleration up here. I didn't do this here. I think I do it in later drawings. But I would want to also put an acceleration. But I do not want to connect that acceleration arrow to this center of mass representation of the object here. I would want that just kind of floating up here to the side to show that this object is accelerating. Okay, so free body diagrams, we draw them with the center mass represented by a circle or square, and we act as though all the mass is there at that center of mass. And that's a fine approximation because the center mass of an object moves as though all the system's mass were concentrated there. Okay, so let's go through the rules of creating a free body diagram, or just like the steps to create a free body diagram. So the first thing you're going to want to do is define what your system is. What is the system or object that you're looking at? Okay, so if we had Mary McNary here in free fall, okay, we would put a box around her. This is what we're looking at. This is our system. Okay, and the rest is just our surroundings. Okay, so we're going to look at all the forces acting on this system, or you could replace that word with object here in this case. Okay, so once we've identified what our system is, we're going to draw a box or circle to represent the center of mass. Okay, then we represent forces acting on the system with arrows, and typically the standard notation, especially like for the AP test, they want you to show that the tails of the arrows are connected to that center of mass. And the length of the arrow is the relative magnitude. So here in this case, the only force, if she's like in free fall, that's acting on her, if we neglect air resistance, right, would just be the gravitational force. So we label that with Fg, because that's the force of gravity. Okay, and then we need to also at the end include our reference frame, so that when we do any calculations using our visual or free body diagram, we know which directions we've called the positive and negative directions. Okay, so if you have an acceleration or velocity, which you would have an acceleration and a velocity in this case, but I just show the acceleration here, you never want to connect that to this object model here. You want to just put that off to the side to remind yourself that it has a certain velocity or it has a certain acceleration that you know. Okay, well, I guess that next slide goes to our next video, so I'm going to go ahead and cut that here. I hope that was helpful, and I'll see you in the next video.